one before lunch.
Hungry.
Lunch is still not here, right?
Yeah, they are. I think it's right in front. The cart is ready.
All right. So, hello everyone. I am Tom from Genesis, and today joining me online is Cece from Allegro. So together, we're presenting the revolutionizing edge computing, AI, and IoT with InfiniEdge AI. So here's today's agenda. So first we'll talk briefly into Project InfiniEdge AI, since Tina kind of walked through most of it, so we'll just go briefly, and then I'll be introducing Shifu, and then CC is going to introduce Yomo, and lastly we're going to show you a demo of everything in action. So first, yeah, InfiniEdge AI. So just wanted to talk about the terminologies because edge is a kind of a broad term. So in our presentation, near edge will be the edge cloud, which is closer to the data center, or it could be on-prem, but depending on the computational resource you have. And far edge devices usually are resource constrained, like a Raspberry Pi or Intel NUC or Jetson Nano. And then for the IoT devices, we refer to them as edge devices. So Project InfiniEdge AI standardizes the way to run, use, train AI at the edge as a whole. And then they also implemented using AI from different providers, such as function callings and API calls. And then lastly, it also includes a IoT connectivity part, which is done by Shifu. So I'll talk about Shifu first. So the problem today is that current IoT system lacks interoperabilities. So you can see we have a bulk of heterogeneous devices. And usually each device has their own siloed system, making it difficult for developers to develop IoT applications. So usually IoT devices and applications are highly coupled. Well, in a traditional way, when we have only just one manufacturing software, it's fine. But nowadays we have ERPs, we have AI models, we have data centers, we have data lakes. So this just won't work. So think of it, if you replace one of the devices, you have to change every single application that interacts with it. So currently this is done by manually. There's no standardized way, and it's a $400 billion US dollar per year problem. So how do we solve it? So quoting from Professor David Wheeler, all problems in computer science can be solved by another level of interaction. So let's think about the mobile development ecosystem for a while. The development costs are relatively low. We have a good ecosystem. If I were to develop an Android application, I don't have to worry about what kind of sensors on the phone or what model of the vibration motor it is. All I have to do is call Android's SDK or API to develop my games. So essentially, Shifu is we're aiming to build Shifu as the Android for AIoT. So by abstracting all the device-specific thing out from applications and put it into a layer of reusable drivers. The layer is Shifu. So Shifu kind of sits in between your applications and your IoT devices. And then abstract IoT devices as a set of APIs. So by doing so, we kind of completely decouples your application from your hardware. So it reduces lifecycle management, and everything we've integrated using Shifu is reusable and it's containerized. And then we have enhanced endpoint security down to the physical connection or up to layer 7. And then superior scalability due to its nature of Kubernetes native. And then we have minimum maintenance. And lastly, it reduces the overall development time for IoT applications. So here is a more detail. I'm not sure if you can see it. So this is a architectural diagram for Shifu. So at the bottom in the square, we have an IoT device whatever it is. It could be running certain protocols, or it could be from a different vendor. And then what is it called? So the middle one is what we call it the device sheeple. It's referred as the twin of a device. So within that, we have the driver of the device, which does protocol translation, and it also does data format. So whatever goes in zeros and ones goes out as formatted. So it could be JSON, it could be XMLs. And on top of that, we have the layer 7 proxy, which is for application development. So from an application, all you need to do is just call the APIs. It could be HTTP, it could be MQTT or gRPC. So, so this is kind of like translation, but also added grammar in. So if we think of protocols as languages, understanding a language doesn't understanding the language doesn't mean I mean you have to know the grammar in order to understand the language, not just the words. So driver does that. So that's how you decouple your application logic, device logic out of your applications. So here is a sheeple in a cluster scenario. So usually on top of it, we have the master node running the custom resource definition, usually a 3-node cluster. For master node, we usually have 3 nodes, and for worker nodes, we can just add in on demand. So the more devices we have, if we run out of resources, we'll just add in one more node. So that node will start connecting to the devices and balance all the workload. Yeah, so today we have about 2 million devices connected with sheeple, and we have about 300,000 instances deployed over the world. And then we are currently in more than 6 industries. So the goal of sheeple is to become the nervous system of artificial general intelligence. You guys will see the demo later, but yeah. So sheeple is an open source project. It open sourced about 2 years ago. We have about 1.3 thousand stars at the moment, about 130 forks. And then since we have an open ecosystem, we already have customers and partners from Fortune 500 companies and industry leaders. And we're also part of CNCF. So sheeple is actually a CNCF's landscape project, and also InfiniEdge AI within LFEdge. Yeah, next I will talk about 2 of the use cases for sheeple. The first one is something we did with the California Strawberry Commission. So California Strawberry Commission is a government-owned agency that forms by the strawberry growers in the US. So if you don't know, California Strawberry Commission contributes to about 90 to 95% of all the strawberries production in the United States. And strawberries, one of the kind of labor-intensive fruits in the world. So it requires a lot of labor work. So the California Strawberry Commission always trying to find a way to digitize everything to help the growers. So, for example, a simple pest control issue costs them about 32 million per year. So, what we've done for this project is sheeple is being installed on one of their tractors, so something like that. And then on the right side is a Raspberry Pi where sheeple is running. So this is the software architecture. But basically, sheeple installed inside. There's a K3s cluster within it, and then connects to all the sensors on the tractors. So by doing so, they can leverage all the data from the sensor to give real-time assist for the growers who is driving the tractor. They call it the growers A. And then in addition to that, they continuously retrieve the data and push it to the cloud, sync it to the cloud for AI training. So eventually they are going to deploy small language models or using geo-distributed cloud, or they're going to change it to maybe a Jetson Orin, so that it is able to do real-time assistance to the growers. So before using Shifu, they have a limited scalabilities. Their previous solution is ESP32 based. So deploying everything manually. So with Shifu, it's actually, there's no limitation to scale because every one of these is self-contained. And then before taking data from the field takes a year to build a pipeline. And now we have about data processing, customizations, and everything ready in 4 weeks.
Quick question. Did you get discount from the strawberries?
Yeah, I was there. I took those pictures.
No, I mean for eat. Did you
Yeah, I
get
did.
it written?
No,
Just kidding.
It wasn't in season last year. Yeah, and then it was hard to integrate to with different solutions, software solutions, and hard to enable AI. And then it requires a considerable amount of manual deployment, connecting sensors and installing the software. And with Drupal, everything is standardized. Everything is a Kubernetes cluster. Everything is a manifest YAML file. And just plug in the USB stick and flash on the OS, and everything is ready. Onboarding is automatic. And then the next use case is a supermarket chain in Malaysia. So they aim to use AI-driven smart carts to drive sales, better manage inventory, and improve customer experience overall. So they were having issues. So they have this Raspberry Pi installed on every single cart. But before they were having issue to deploy new features because they have to do everything manually, copy and paste binaries and stuff. But with Shifu, everything can be deployed within hours, and then you can roll it back instantly. And then before they were having issue integrating AIs, so they're having a hard time doing the conversion. And with Shifu plus Edge AI at the store, they're able to increase the conversion to 15 to 30%. And then before everything is transmitted to the cloud all the time. And now 80% of the data is processed at the edge on each card. So it lowers the cost for them and also improves the decision speed, responsiveness. So this is their setup. It's a 3-tier setup. On the cloud, it's centralized for all the supermarket chain. There are management, retail on top of it. And then at the near edge, so every store, every supermarket is in near edge. And then the for the far edge, it's the cart. So the cart is a worker node in this case, and then the near edge is the master node. So the worker node joins the master node. So they're all in the same Kubernetes cluster. And then each store has their own edge AI and cart management services, and Shifu is installed on the terminals to connect to barcode scanners, and also on the cart for the different sensors like the display, alarm, beacon for positional data, and battery sensor information. Yeah, so that's for the Shifu introduction. Now I'm going to hand it over to CC.
Okay. Thanks, Tom.
Thank you.
Hello.
It must be very late there.
Yeah, CC is in Beijing, so it's like, I don't know,
Yeah.
3 a.m.
Okay. Hi guys. I'm CC from Allegro. This is the first time I know CC means confidential computing from Wenhui. Yeah. So I know you guys are hungry right now. Believe me, I'm sleepy. It's definitely a time and space problem. So today we discuss geo-distributed computing. Geo-distributed computing, we all know these words, but I think in the past 30 years, distributed system is it must be misunderstood because generally speaking, what we talk about distributed system means distributed in data center. Like Facebook, like Instagram, all applications did that because there is a database. I started writing code from 1998, and what I learned first is called Foxbase, a database software. And I think from today I can get rid of database because of database, we built API on top of it, and then we built our application. So the data must be exchanged between servers less than 7 million seconds. That keeps the distributed system healthy. But if we deploy our services applications around the world in different data centers, the only problem we got is time and space problem. If we can solve the problem, we can build a geo-distributed system. So people can put their request to the data centers close to them, so they can get the fast response and more secure and like GDPR compliance system. Okay, Tom, can you help me to next page? Okay. About 2 hours ago, OpenAI released a new model called OpenAI O1, and have O1 preview and O1 mini, 2 models. Today, when we talk LLM, everybody want improve their accuracy and improve their speed. We need the LLM answer our questions correctly and low latency give me the answer. In the past 20 years, I've wrote a lot of systems, but at that time, I used a word called loading instead of thinking. Today, the slow response of LLM get a new name to take place of the loading. It's called thinking. Thinking means the LLM is very, very slow. Tom, can you help me to next page? Okay, for accuracy, in the past 2 years, RAG is very popular, but uh, I wanna introduce a function calling uh, to guys because RAG is useful for static knowledge data, but when we build a completed system and a production grade system, we have a lot of things to do, like real-time data retrieval, real-time request data processing, and interacting with external APIs. So function calling make a great way to meet these requirements. And the next page. But but when developers implementing function calling, it's very difficult. First of all, like OpenAI GPT model, if you wanna put your APIs connected to GPT model, you have to write code like this. Say there are 2 functions built as tools, then put all the tools to the prompt, and then we request the GPT model. I don't think any senior developers want to write code like this, because you have to put all your tool calls to the application code, and you cannot do unit test and evaluation properly. And for next page, we will say Google Gemini function calling is way harder than OpenAI model. And the next page. So so we are thinking, can we uh, improve the developers' experience on implementing a function calling if they can write once, run on any model? That would be easier. And I want to introduce strongly tapped languages to function calling because Python and Node.js are great languages, but in production environment, we usually use more static tapped languages for more uh, uh, high availability. So let's see an example. If I wanna add a function to OpenAI model, the feature is when user ask website, I can give the latency measurements of the domain. Uh, I, I read this demo by Go language. This is a common function called a ping. The parameter is a domain, just a string. So I will ping this domain and put the result back to LLM. So LLM can get any website the ping results for me. And the next page. What I do is just to write a function called description and return a string. In this string, I just described how this function uh, 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 do the requirements. I just write if user asks IP or network latency of a domain, you should return the result of the given domain, and try your best to dissect user's expressions to caption. The description is the domain of the website. That's all. And in next page, I just implemented the handler function, and in this function, I use context.read LM arguments to get the arguments given by OpenAI LM model, and I put the result of the ping by context.read LM result, then read back to OpenAI. So next page. Um, so by this, just about 30 lines of code, I just write my first function calling serverless, and I can run on my own dev machine or deployed to many data centers around the world. And when I ask compare Amazon and Shopify network performance, LM will infer Amazon.com and Shopify.com to the function calling, and the function calling did the ping command and give the result. So the LM can answer these questions with my function calling. And next, in UMO, there are two features. One is LM bridge. For this feature, we built a gateway to many LM models with popular LM models like OpenAI, Ropic, Google Gemini. So developers do not need to change their application code when they want to change to another mode to try the new features. They just change it in the LLM bridge. So their code, their application do not need to change. And the next page, is serverless LLM function calling. We make LLM function calling can be written and collaboration in serverless way. So we can build secure function calling, especially when we want to access private data in our DMZ. So we can decoupling function calling from application services as our infra, and we can manage them DevOps and collaborative development and debugging unit testing, so that we can build a production-ready system by this. And next, is we can build all our LLM bridge and function calling to many data centers at the same time, and the users will automatically be routed to the closest data centers, just like a user from Spain will be routed to German or France data centers. And currently we have 6 data centers free for developers who want to try VivoGrid and UMO. And next. Okay. Okay. That's all. Back to Tom. Thanks.
All right, thanks, Casey. So last I'm going to show you the one in action. So it's a pre-recorded demo. It's 2 parts. The first part is Shifu integrating devices and in real time. And the second part is the function calling feature. So, what the hell? All right, this one. So, to run Shifu, you need a Kubernetes cluster, which we created using Kine for this demo purposes. So, by creating the cluster, you can see we have all the system services, and also we have just one node that's running on a laptop. And then the architecture looks something like this. So we have an empty cluster, and we have 3 devices. One is a RDSP camera, the other one is a Siemens PLC, the third one is a LED display using OPC UA protocol. And next, I'm going to deploy Shifu and Ingress. So Ingress is being used for exposing my services to the public so that AI can connect to it. And then the second one is Shifu, which once deployed, you have the capabilities to spin up the device Shifu, which is the digital twin of the device. Yeah, so, and then after that, the cluster looks something like this. Yeah, still, we're not making connections at the moment. And then next, we'll spin up all the digital twins for the devices. And then similarly, it can be done by just one command line. But firstly, we need to create a secret for it. So that's a secret for the IP camera. And then we're going to deploy everything within the device Shifu folder, which is all the manifest files for all the devices. And then lastly, we're going to apply the Ingress configuration that exposes all the devices. So as you can see, we have all 3 devices deployed up and running. And then edge device is Shifu's custom resource definition in Kubernetes. So each physical device will be an edge device here. So after that, your architecture looks something like this. Yeah, so all the twins has been deployed, and then now you can actually interact with the device. So the first device we're going to interact with is the camera. So we just copy this string and put it in to our browser. So you can see everything is running. So that's the first device. And then on the left side is the PLC, and the right side is the LED display. And then to control the device or get data from the device, all we need to do is use HTTP post or get. Okay, and now let's do a post to the PLC to turn one of the lights on. So that's one of the output. So you can see it's on, and we can turn it back off. So the light is off. And then we can try modifying the LED display. Same, we're going to use post with the JSON. We can change it to like 39.99. And that's that. All right. So this is the flow of the data. So from the terminal, we have the curl command, which is the HTTP get, and then it enters the ingress, and then enters routed to the corresponding pod, and again within the pod, the curl command gets translated by the driver into an actual PCUA command that gets the data from the device or sets the data in the device. And then the second demo is with function calling. So now we have the cluster set up. We're able to do function calling, but this demo uses OpenAI. We also have one ready that's using YOML, as CC just presented. We'll be giving all the links for those two repos in the next slide. So yeah, this is just setting up the OpenAI client for the endpoint and also the API. Then next, I'm going to define my functions. So as you can see here, all the functions calls to the devices are just one line of API calls, basically. So that kind of simplifies your whole IoT development. And then next, we're going to define the tools, which is the description for the function, and also if the function takes the parameters, we're going to describe the parameters and its type and what it does. And then next, we're going to write a function called handler. Basically, when AI returns the function name and its parameters, we have to find a way to handle it. So that's that. So after that, we're able to call GPT to take a picture. So the setup looks something like this. So our function calling services sits outside the cluster, and it's interacting with OpenAI, and the input takes is natural language. And then the first thing I asked OpenAI is, hi, can you tell me what the camera sees? And then OpenAI is able to automatically find the suitable API endpoints and call that API. And then it calls the get image function, and then the HTTP route goes into ingress and then turns into RTSP. So we have an image. And then next, I'm going to pass the image back to the chat. Basically, I'm trying to ask, can you tell me what's in the image? Specifically, what is the number on this display? And then does the PLC has 4 output lights on? Now, this is important because we're going to use this context to do our next function call. So we're going to run this. So it's going to take some time. And then the first return is the display shows the number 39.99, which is correct. And then the second one is the PLC has one green light illuminated, indicating that it is on, but I can't confirm if all 4 output lights are on based solely on the image. So that's one of the limitations of the model itself. So we're just going to call it again to see if it can be said about the result. Then after the second call, still for the PLC, it appears that only one light is on, so that's good. And we're going to use this into our next chat. So next, I'm going to ask AI to increase the LED display number by 5. So we're going to pass the image into OpenAI, and OpenAI is going to read the image from its GPT-4o model, and then add 5 to the number, and call the relative function with the correct parameters. So in this case, it sets number and then turn into 4004. And then the next one is PLC output. So the message is, can you set the PLC output to true if it doesn't have 4 output lights on and off if it does. So this is going to do the same thing. So AI has to kind of think and then understand the image first to make a decision. And it says, since it's off, I'm going to turn everything on. So that's a function called by the AI. And this is the, yeah, that's the flow. So this is just a quick demo using OpenAI, but by leveraging YOMO and add it into this project, we're actually, we can put everything we define, the Python, the function calls, a call handler into just one app.go, and then run it using YOMO so that it will be LLM agnostic. So everything you define can be used by either OpenAI, Gemini, Anthropic, or even Code. I don't know. So yeah, that's the demo. And then lastly, we have put on some resources. So if you're interested, we have the InfiniEdge AI project, Shifu project, Yomo project everywhere. And also all the demo files we've used will be available through these links. So yes, that's it. Thanks everyone. Questions? Like around here. Go ahead.
You have to have an IoT device with the Linux, is that right? You can do more than Linux. For example, ESP32 is smaller than that.
Are you asking about people or the device?
So what I see is you deploy a Cupertino sorry, node for the system. I think these need to be a Linux system, right? There's nothing lower than Linux.
Yeah, but we don't deploy on IoT devices themselves. We deploy on the far edge node or edge node. Yeah. So where it could be a Raspberry Pi that connects to a sensor. Yeah.
But also some sensor has a microsystem.
Yeah,
which is
those we can't install anything on.
So the lowest level, if
If
you
now
have to have
require
a,
Linux or a Kubernetes runtime to operate.
So you don't really need a driver for local IoT device, right? You just send the command over, right?
Yeah, so the driver will be embedded inside Shifu, so it is able to communicate with the devices using their native protocol or language, but you still need the driver, but the driver can be anything, any language, as long as it's containerized. We actually have a tool for generating drivers, but it's not released yet. Yeah. It's lunchtime.